Welcome everyone to the latest Trees Around the Globe Student Research Campaign webinar. This is webinar number 84 for the campaign. We are in the second to last month of year 7. And today, this is the State of Trees, August 2025. Today is Wednesday, the 27th of August, 2025. Today, we'll be talking about looking at trees, vegetation, land cover, and more with future NASA Earth observing missions, NISAR, GRACE Continuity, and Landsat Next. And we have some great speakers today, and also we have a recording, and I'll talk about that in a few moments. But let's get on with it because we have some great live speakers today to talk to us about these missions. But before we go on, as you know, I always like to find some really cool, pertinent, and nice quotes to talk about with some famous folks from the past who are always either in the science, mathematics, education, things like that. So I have 3 here that I thought were relevant to what we're going to be discussing today. The first one is from Dr. Rosalind Franklin, who is a British chemist and X-ray crystallographer. She said, "Science and everyday life cannot and should not be separated." Okay, these are just ones we don't talk about. These just ones on just to put in your head, just to think about. The next one is from Louis Pasteur, a French chemist and microbiologist. "Science knows no country because knowledge belongs to humanity and is the torch which illuminates the world. Science is the highest personification of the nation because that nation will remain the first which carries the furthest the works of thought and intelligence." Pretty prophetic. And the last one from Sir William Lawrence Bragg was an Australian-born British physicist. "The important thing in science is not so much to obtain new facts as to discover new ways of thinking about them." I thought these 3 quotes were very poignant, and I just, I always try to find, some from some folks that we haven't heard from a while, but have been in the science world and in our thoughts, in our thoughts, and have been, very, instrumental to, the pursuit of science over, over the last, from the history of science on our planet. So, think about those. Those you can check those out when you look at the recording for this webinar. And I should mention, as you know, I always get the webinar recording up, soon after the webinar is over, but you won't see it until at least later tomorrow, or most likely sometime on Friday, most likely Friday morning, because I won't be able to get it up because of the website maintenance. So it'll be up on Friday, probably Friday morning at some point, and you will see an email being sent out to you to let you know that the recording of this webinar is online. All right, today, okay, after the introduction and the agenda, this housekeeping, and some of the metrics, we're going to first hear from Dr. Felix Landerer, research scientist and project scientist for the GRACE follow-on mission in the Sea Level and Ice Group at the NASA Jet Propulsion Laboratory. He's going to talk about that, the GRACE Sea mission. I should also mention he is a project scientist for GRACE Sea mission as well. He is at the NASA Jet Propulsion Laboratory, where our own Peter Falcon is based, and he will be talking about that mission, followed up with Professor Peder Nelson, as you know, senior instructor, senior faculty research assistant too at Oregon State University. Also, he is the OregonView state coordinator, the College of Earth, Ocean, and Atmospheric Sciences, Oregon State University, Corvallis, Oregon. And then we will hear a recorded presentation from Dr. Erica Podest about the NISAR mission, the NASA-ISRO Synthetic Aperture Radar. Now, this is a recorded presentation. It is pulled out. It's a shorter version pulled out from her November presentation because she is currently on travel doing research, I believe, in Peru right now. She was at the NISAR launch, but she is in the field right now. But as you can see here at the bottom of her presentation section, she will be joining us live to talk more in detail about the NISAR mission at our next webinar, which will be the 16th of September, 2025. So please come back for that, because she's going to be talking a lot more about the NISAR mission since it was recently launched just last month. So please come back for that. But we wanted to include this here and end with this presentation, with this recorded end with this recorded presentation, so it will set it up for her part of the webinar on the 16th of September. So we will be, talking about all these missions today, and then we will then finish it up. I will talk a little bit about next month's webinar as well, the one for the 16th of September. So we have the map of the active countries for the Trees Around the Globe Student Research Campaign. We have participants who are active from 70 of the 127 globe countries. So we are still excited that we have great participation from the countries that are in green are the ones that are active in the Trees Around the Globe Student Research Campaign. And as you know, I always bring these metrics in. These are numbers now. These numbers aren't up to date as of today, even though I have on the next slide they're up today, but these are from Monday before the website went down for maintenance. I grabbed the numbers Monday morning before it went down, before I could access the actual the ADAT system and the API, so I could get the numbers. But as you can see here, we are in year 7, and in year 7, we are just over 37,000 measurements from tree height, land cover, and greenings from just over 11,200 global sites. And for the full campaign, we are over 246,000 observations from over 75,000 global sites. And even though I have as of 27 August, I probably should have put as of the 25th of August, since it was Monday when I got the data. But we are at 84 webinars, and we've actually had 32 special webinars. And these are webinars that include ones that we've given as part of the campaign to different countries. I just gave one, and Peter Falcon was part of it on Monday, to Globe Africa, because Globe Africa is running an intensive observation period during the month of September to support the JEDI mission to compare tree height observations with the JEDI mission data as part of a group at I believe it's Northern Arizona University, and a project they're doing to do some comparing and validation of the ground of the satellite data, the instrument data from the JEDI mission that is currently on the International Space Station right now, taking tree height measurements basically between 56 degrees north latitude and 56 degrees south latitude. So they're focusing on those regions as well. And once the Globe website comes back up, if you go to the Globe website and you go to the news section on the left side, kind of in the middle of the page, there is a news article there that you can click on that talks about the Globe Africa Intensive Observation Period, or IOP, that you can read more about this. And even, some of you may be in this area where they're looking for this data. It's being hosted by Globe Africa, but you can check it out because you may be in this, latitude zone that it's looking for. They're looking for data from all over this latitude area. It's just being hosted by the Globe Africa region, which they're looking for most of the data, but they're looking for data all over the globe to, in this latitude, sorry, not all over the globe, over this latitude range to use for the JEDI data comparisons. So check that out when you get a chance. Okay, so today we're going to talk about 3 major missions. Okay, one is the NISAR mission. You can see here, and these missions that we're talking about today, I have squared off here in the green squares. We have NISAR, which was launched on the 30th of July, 2025. And we have GRACE C, which is GRACE Continuity. And we have Landsat Next. All right, so we are going, and this here is the current Earth fleet, okay, that we have, in space right now. And we can see all the way back from 2000. And as you move around this spiral, all the way to the ones, and all of these are color coded from ones that are, ones that are flying right now to ones that are being, ones that are extended, meaning they've been in space for a longer period of time, ones that are operating. Extended means they're operating but have been in space for a while now, operating now that they're operating in space right now, but of a younger origin, ones that are in implementation phase, and ones that are in formulation phase. So you can see here the color coded from blue to green to orange to purple. So the purple ones are the ones that are further off, and then it goes back to the orange and to the green and then to the blue. Blue are the ones that are the oldest ones in space right now. So we are going to start, though, with the GRACE C mission, and we have with us today Dr. Felix Landerer. So Peter Falcon, if you could do a brief introduction to Dr. Felix Landerer, and then we will pass it over to him, and then I'll stop sharing them.
Sure. Yeah, thanks, Brian. Happy to introduce Felix. Somebody I work with for many years here at NASA's Jet Propulsion Laboratory. He is a research scientist at the JPL's Sea Level and Ice Group. You can just read through his bio very quickly. His area of specialty is hydrogeodesy, as he calls it. So basically, he studies anything water related. Water cycles, sea level, ocean currents. His research interests are evaluating global and regional sea level variations from satellite and in situ observations, tracking Earth energy's budgets, ocean heat content from satellite gravimetry and altimetry as well, data, and Earth's water cycle and associated water surface mass redistribution. And as I look through his bio, he has a very impressive amount of publications, as well as NASA and JPL awards. So congratulations for those, Felix. And as Brian mentioned, he is also the project scientist for the GRACE Follow-On mission and the upcoming GRACE Continuity mission. So with that, I'd like to turn over to Felix, and thank you once again, Felix, for being here with us today.
Thank you, Peter and Brian, for the introductions. Let me share my screen, go into presentation mode. Can you see it all right?
Looks great.
Thanks, perfect. All right. Well, thanks for the introduction. So I'm joining you here today from my office in Pasadena at the Jet Propulsion Laboratory, where I work with a fantastic group of people, about 25 to 30 people on these missions, GRACE Follow-On and GRACE Continuity. And although Peter highlighted my achievements and publications, it's really always teamwork, starting with engineers that build these missions, build the instruments, scientists that work on the concepts, on the ideas, and then we work together and make this a reality. So this is really teamwork, and that's a huge part of why I love this job, why it's so much fun. So it's a pleasure really today to talk about what we do with these missions a little bit. I'm going to talk about tracking Earth's water with the GRACE series satellites since 2002. So we've been doing this for almost a quarter century now, 23 years. And when we think about tracking Earth's water, as this slide builds up, Earth's water comes in many shapes and forms. It's liquid in the ocean, it's frozen, ice sheets, glaciers, snowfalls. We use water for irrigation. We pump it from the ground often, and increasingly so. It is also about the absence of water, where we rely on it, or where we used to have it. Water obviously is essential for the global ecosystem. This series here is focused on trees, and I won't be talking about individual trees or even forests, but obviously water is highly relevant in this context, as it is tightly coupled with the carbon cycle. So when you think about water and its distribution, and think about it from a remote sensing point of view, so trying to observe it from space, from high up, you immediately run into a challenge, which is, how do you observe this? What measurement technique do you use that can observe both snow, maybe seawater, rivers or surface water, maybe water that's kind of hidden under the canopy of trees, or that's in glaciers? And it's hard to find one measurement in the typical sort of spectral domain, where you bounce maybe a radar pulse off the surface of it and try to measure, how much snow is there really? You might get an impulse signal, but it's hard to actually gauge how much water there is. And it's even more difficult when the water isn't visible, when it's deep underground in groundwater. But there's one unifying characteristic that this water has, in fact, that everything has, which is gravity. So it has mass, and as such, it has a gravitational field. And if the mass distribution changes, the gravity field actually changes. So we have devised this concept of two satellites orbiting about 500 kilometers altitude, following each other 200 kilometers apart. And as they orbit, the distance between them changes ever so slightly. And that's shown here. They're not tethered. In the middle, you see a microwave and a laser signal. And these satellites, as they orbit, they don't look down. They just look at each other and measure the distance changes as they orbit the planet continuously 24/7. They're in a polar orbit or near polar orbit. And when we compile all this data, in the end of the day, we get these maps of what we call water mass changes. And I'll dive into that a little bit more, just how that works and how we do it and what we've learned since 2002 and why we're still doing it and going forward with the GRACE Continuity mission. So this is really a unique concept. We're not looking down. We have two satellites looking at each other, just tracking these distance changes. And these distance changes are very small on the order of microns, kind of thickness of a human hair. So like I said, these satellites orbit in a polar orbit. We get about 15 complete revolutions per day. You stack that over time. And once we have a set of about 30 days, so a month worth of data, we have enough data to devise a global map of the mass change. And when you look at these maps of gravity, for example, in August 2006, so this is data taken by the original GRACE mission, it kind of looks like this. And we repeat this measurement on the right side here in September, and then we compare it. And when you look at these maps, we look for differences. Now, you'd be really hard-pressed. You can stare at this all day and see actual differences. These maps look very similar. However, when I difference them, I subtract September from August, this picture emerges, very different. All these features that you see in these what we call static gravity fields, they disappear because it's static, they haven't changed. And now we have zoomed in. We also need to zoom in to the scale by about a factor of 1,000,000, and we see very different features. The features here, these stripes, that's the Andes, so that's related to plate tectonics and topography. The mountain mass is what you see in the gravity field. Obviously, that doesn't change so rapidly. It changes on geological timescales, but not typically from 1 month to the next. What does change from 1 month to the next, though, is mass here in the Amazon basin. And this is a decrease in mass. So as we go from August into September in this particular example, the Amazon has lost mass. And what this is on the ground is part of the typical standard annual cycle, the hydrological cycle. It has rained up until about July, August, and now the dry season comes, the rain stops, but the water evaporates and runs out through the Amazon River into the ocean. So the Amazon is effectively losing mass, and this is what we detect. So we can now track this globally month after month, and we get a very accurate picture of how these mass patterns are changing. The mass doesn't it doesn't disappear, obviously, it's conserved globally, but it is redistributed constantly. It evaporates over the ocean, it rains over land. So we get this picture of the global water cycle. And like I said, we've been doing this for almost 25 years. So we get a very good sense of the global changes that are happening, and we can understand the mechanisms, the processes, and we can relate it to other things. I'll get into that a little bit, kind of wrapping it back to maybe vegetation and trees and land cover in general. Just stepping back a little bit, I mentioned the original GRACE mission, so I just want to highlight here the series of GRACE satellites that we have had, that we have, and that we will have. So we're in a very fortunate position that we have this collaboration between the US and Germany, the German Space Agency. They collaborated on the original GRACE mission that lasted from 2002 through 2017, excuse me. Then in 2018, there was a slight gap. We were able to build and launch the GRACE follow-on mission. So that's ongoing right now. We're literally taking measurements today, tomorrow. We're processing the data. We're putting that out for you to use. This is, again, a collaboration with Germany, this time with the GFZ, the Helmholtz Center for Geosciences. I'm also wearing another hat. We're working on the GRACE Continuity mission that was already mentioned by Brian. So that will launch in 2028. We hope to have no gap between these missions. Typically, a lifetime for these missions, very conservative, is 5 years, but we typically are able to extend these to 10, and in the case of GRACE, even 15 years. So 28, GRACE Continuity will continue. Actually, the satellite is being built as we speak by colleagues here at JPL in Germany. The platform is ready, and we're integrating the instruments, and it's going to go through some testing. And then in a little over 3 years, we're going to launch these two satellites to continue the measurements. continuity is kind of a theme for this entire data record. I'm showing you all the GRACE months in a global map in this kind of postage vignette type plot. You can't really see any details. That's not the point of this plot. The point is just that we have this continuity of data. Your years run horizontally, the months vertically. There are some gaps. That just happens when you operate satellites. You sometimes run into issues that we work on, we try to fix. We had some issues with GRACE where the battery was being iffy, so we had to pause it once in a while to allow for enough recharge. But we really try to make the most of these really expensive investments. But once they're up in space, they provide so much value at pennies to the dollar and what they cost in development. And the return of investment is really fantastic with the continuity of the data. I mentioned the gap between GRACE and GRACE follow-on. So GRACE follow-on began here in 2018. We also had a little bit of an issue at the beginning. We checked out an instrument, fixed it, and ever since, it's just accumulating data. You can also see in the background, maybe if you squint your eyes, that the color scheme is changing slightly, sort of from an orangey red type to more blue. What that is really in the background is the change, the global change on a global scale here that you see. This is water being lost from the continents, mostly ice melt, and being accumulated in the oceans, causing sea level rise. I'll talk about that in a little bit. So in terms of data and science and applications, that what you can do with these observations, I'd like to think about the GRACE missions really as smart water meters for monitoring drought, flood risk, changes to groundwater, sea level, glaciers, on a monthly timescale. So you see here sort of in a schematic, the Earth's water cycle. Water is continuously cycled, heated by the sun over the ocean, evaporates. Most of it actually precipitates over the ocean again, but obviously over land, it rains as well. It accumulates, it snows, snow melts, it drains back into the ocean, and the cycle repeats. It's not the same every year. We have seasons of droughts, we have floods. And as these patterns unfold and as they change, we learn more about how to deal with it, how to adapt, and how to just be smarter using the water and mitigating risks that are associated with some changes. So for the remainder of the presentation, I'm going to jump through these examples a little bit, show you the data that we've accumulated, what we've learned, and I'll wrap up then in the end with pointing you to where you can play around with the data yourself and get your feet wet, so to say. So one of the most prominent examples here is the ice melt that we have over Greenland and Antarctica. We've recorded this since 2002, and for the most part, these ice sheets are losing mass. You will see these color or these maps, being colored in with orangey to red colors. Those are regions that are losing mass, and overlaid are the ice flow patterns. The ice may look static as we look at it, but it's also constantly flowing, or creeping rather, towards the ocean as it snows and then gets compacted and again drains into the ocean. You see that for both Greenland and Antarctica, these emerging hotspots of mass loss concentrated near outlet glaciers. This is one of the profound findings and sort of mechanistic understandings that we've gained with the GRACE missions and combining it with other observations, that as the oceans warm right near the outlet glaciers, this is where the glaciers are in touch with the ocean. As this ocean water warms, there's a tendency for the glacier to accelerate into the ocean and melt faster. Doesn't really sound like rocket science, but by quantifying these processes, we're able to also project that into the future and understand better, what is the risk of sea level rise in 10, 20, 50 years, given these processes. You can also see that in Antarctica, there are regions where mass is growing. You see some light blue shading here on eastern Antarctica. This is also an effect of an accelerating water cycle. A warmer atmosphere can hold more water, more moisture. That means it can also precipitate more. In Antarctica, it's still cold enough that this precipitation falls as snow, so it actually accumulates in these regions, but it's offset in the net by the melt on the western side. For the last few years, though, it's been somewhat flat. So we're watching this. We've had periods before where it's flat and then it kind of accelerates rapidly. So this is why it's so important to have continuity of measurements. And if you have gaps, you're just blind to that process. And you can grab these videos, by the way, by going to this website here that I've linked below. And there are a lot more. Oh, I should say, I forgot to mention the mass change. We typically quantify, especially for these ice sheets, in units of gigatons. So that's a kind of a unusual unit if you're not working in this field. A gigaton is 1 billion tons of water. And that's always kind of hard to wrap your mind around what that is. Here's just an aerial view of Manhattan in New York. If you put 1 gigaton of water on Manhattan, this is what it would look like. So if I jump back here to my time series plot, you see that Greenland alone in the last 23 years or so has lost over 6,000 gigatons. So now imagine stacking 6,000 gigatons or taking them off of Greenland, and you put them in the ocean, they get redistributed, and sea level goes up accordingly. So just a sense of scale here is always really important to understand what you're looking at. I've also mentioned already the acceleration of the water cycle as global temperature goes up. So in this plot that I'll play here, it's an animation in a second, you're going to see kind of bubbles popping up everywhere on the map. And what this visualizes is we've taken the entire data record, 23 years, and we've mapped out water extremes on the high and the low end. So drought and floods. Think of droughts and floods and how they appear and disappear over time. And then on the lower right, you can see the total intensity of the combined extreme events. And let me just play that, and I might play it twice so you can appreciate how this unfolds. You see these bubbles popping up. So the size of the bubble correlates to the size of the event. And as time goes on, you see these bubbles appearing more frequently on both the red and the blue end of the spectrum. So both more droughts and more floods. And that is driven by just a warmer atmosphere in general that I've already mentioned, right? It just can hold more water, but it can swing into both extremes faster. So you see all these bubbles here at the end of the map. 23 was a pretty extreme year. Some of it is driven by natural climate phenomena related to ENSO cycles. But, these are bubbles on a map. But what this really means in the visualization, what this really means in terms of impact on the ground, and this is where it's relevant for other fields, if you have an absence or a lack of water in very forested areas, here, for example, in northern Canada in 23. So this was a very dry event. You have weather, you have lightning, and now all of a sudden this forest is dry enough that you can ignite these fires. And, you might say, well, this is far away from civilization, people won't notice. Well, the smoke doesn't stay in that area, it travels. So here you can see the air quality map. The fires are located up here, but the winds actually shifted this smoke way into the northern US, across big cities. It eventually ended up all the way in New York and DC. So even though these people are hundreds and thousands of miles away from the source of the event, they're impacted by it. So understanding this and projecting the impact is really relevant in these teleconnections. So the effect from the event occurring here and then having impact somewhere else is relevant. Conversely, at that time in 23, Italy had a lot of floods, made it into the news. So these rapid precipitation events overwhelmed an infrastructure that just wasn't built to the capacity to quickly drain this rain, right? So it causes havoc in civilized areas. Cities get flooded, crops get flooded, and they get damaged. So massive impacts here from these events. So, as a scientist, we like to understand the phenomena, but for our society, it's really providing an additional layer of information, and we call this sort of water intelligence from space, right? We deliver crucial information on water availability, quality, and the distribution, and that can inform water management and set us on a sustainable path for economic development. Very important that we link back what we observe in nature to our society. So I'm going to somewhere that's kind of close to home. This is California, Pasadena, or the LA area is, let me get my bearing right, that's down here. So we're kind of sitting right here. Just north of us is a large area known as the Central Valley. A large fraction of the US's fruit and produce gets grown here in this valley. It's very productive in terms of soil. What it lacks is actually a good source of water. It tends to be very dry and hot in the summer. So there's an aquifer underneath, so deep groundwater. So we've turned to using that groundwater. And you can see a time series here in yellow over the last 23 years or so, how this is developing. The annual cycle, those are the rapid ups and downs. So we get most of our precipitation in the winter. Some of it is rain, some of it is snow in the mountains. Then it melts, drains into that area and gets used. But when there's a lack of snow, so we have years, for example, here in 2013, we have very little snow accumulation, right? From the bottom here to the up is even, maybe a third or a quarter of the wettest year. So when that doesn't happen, the next growing season is impacted because the reservoirs tend to be empty. There's a competition for water from farming, for human consumption, for industrial use. So we can turn to groundwater. But if we pump too much groundwater, then overall the long-term trend is downward and negative. So what we're studying now, and we're collaborating with the Department of Water Resources, the United States Geological Survey, is just understanding how we can do this groundwater use more sustainably, such that when we have really wet years, like this one in 22, 23, with massive amounts of water accumulation, that this water doesn't just drain out into the ocean. We can actually manage the aquifer actively, meaning pumping it back into the ground, and kind of like a savings account for dry years. So, but in order to do that, you need data, you need to quantify it, and this is what these missions provide. So going forward, and this is kind of maybe an outlook already to some of the other talks, especially Erica Pedet's talk with NISAR, because we observe gravity from space from an altitude of about 500 kilometers, our picture of what's happening on the ground tends to be somewhat coarse in terms of resolution. But we need the information at more regional, local, smaller management type scales. So this is where the combination of data fusion or data assimilation becomes very powerful, where we combine one data type with another, fuse it in a hydrological model maybe, and the sum of the parts is more than the individual parts alone. And we can actually downscale this to more manageable kind of pixel size regions that map into where the management scales are. So this is becoming very powerful, very advanced. Of course, there are connections to machine learning, AI, lots of progress happening in this field. And we really want to give the data, make it actionable, ideally, to the field size scale, and that's what's happening. So here's just some missions mentioned here that each provide an individual piece. Evapotranspiration you can infer from eco-stress, so that's really relevant for the current health and state of a plant. Groundwater, that's my turf, my domain, Grace follow-on. We also have GPS sensors that measure the deformation. We combine this with snowpack information, surface water. We now have, there's a data service called Opera. We now have SWAT, a new mission that was launched a couple of years ago that can measure stream flow very accurately. And we're going to get more SAR-type observations of the surface in general, in particular now that NISAR is up. And we're really looking forward to use that and fuse it together and provide even more informative data types. So speaking of data types and data, this is my last slide. I'm going to wrap it up here. I just wanted to highlight where you can actually get access to Grace and Grace follow-on data. So we at JPL here have one interactive data tool. The link is here. You can take a picture of the QR code and you can go there, and I'm going to try this, see how that works. So this is the data tool. This is the website. So I'm going to go on it now live. So when you go there, you get a little welcome tool, walks you through the functionality. You can read that. I'm going to just click that away, but you can choose. It automatically pre-populates the map with our data layers. And then you have the capability here to select some river basins. For example, let's say the Nile. We want to plot the Nile River of Grace data. So from 2002 all the way through June this year, it gives me a time series. You can do some filtering. I can take out a seasonal cycle, and you can also download the data. So this is really a very quick way to access the data, kind of get your hands dirty, so to say, here, and start playing around with it. have your students look at it. The website itself provides a lot of resources, background information about the missions, GRACE, GRACE Follow-On, GRACE C, about the technology. There's a lot of other data products here that you can browse and peruse. So yeah, with that, I'm going to finish here, and I'll take some questions. And if you want to reach out to us, if you're not watching this live, you can also reach out here through our website. Frequently asked questions. There'll be a form that we get. So thanks for your attention.
Felix, excellent presentation. I thought that was really great. Thank you for being so great. There are a couple questions in the chat that I'd like to address with you. I'll just read them off. The first one is from our colleague Lewis from Portugal. And he asks, he says, like, my country, Portugal, is totally devastated by forest fires. And that for sure has a lot of consequences on the environment and otherwise in the retainment of water in the lands. Could this project advise our government could this project advise our government to change the actual policy, changing minds, implementing new methods of work to protect forest landscapes? He says he tries that with work every year with my students, preparing them to be more aware about the environment, in this case, trees and forest.
Yeah, great question. Thanks, Lewis, for joining. So, we don't advise governments directly. We're focusing really on providing the best data products. We work with a lot of stakeholders. So governments are stakeholders. We work with entities that use our data, that manage water resources. We interact with them and try to provide really useful products in a timely manner. So the data latency, we're trying to reduce that. And right now the data is up and out until all the way through June. We're working on July. So like I said, the information content that's in the data that can lead to action is there. It needs to be taken. We try to educate people to understand what the data means. And in that context, it's actually very helpful for us to hear back, to get feedback from people like you, how you would like to use the data or why you can't use the data, so we can see if we can improve how we present it, how we make it accessible. We're increasingly also providing open data tools. So this here is a website, but we're also providing Jupyter notebooks, in particular, for up-and-coming students that are savvy and working with these tools, open source tools, and that can get integrated into machine learning AI. So really love to hear feedback from you, from people that are on the ground. You're seeing the impact. I hope that answers your question a little bit.
Oh, yes, looks like Liz says this. Another question for you. When we think about GRACE, which was up there for 15 years, GRACE Follow-On, and now GRACE Continuity, which is going to be launched in 2028. What are some of the technological advancements in making the measurements, but also making sure we make the same measurements, measuring apples to apples, but also adding new bells and whistles, so to speak, on these instruments?
Yeah, that's a great question. So if you compare the pictures between these missions, they all look similar. Because the shape of the satellite is sort of very streamlined, right? We don't have long solar panels sticking out because we don't want anything to flap. We need a very quiet observation environment. But there are technological advances over time where we refine the measurement. In particular, on GRACE Follow-On, we used for the first time in space a laser ranging instrument. So on GRACE, the first mission, we only had a microwave. And on GRACE Follow-On, the laser was devised as a technology demonstration. So we matured it enough, and it was actually very successful in its rollout. And on GRACE Continuity, you'll see, if you look closely, that microwave, that white line, isn't there anymore. So it's just going to be the laser on GRACE Continuity, and that will afford an improvement in the accuracy of the ranging measurement, which we can build new data analysis pipelines out of that. Under the hood, there are also upgrades that aren't so visible here, just refined instrumentation, better batteries, of course, higher accuracy, GPS receivers, things like that. So At the same time, people are working on already the next generation of these type of observations. We've learned now, we've seen that observing gravity changes, you can do a lot of research with. The next, so the frontier is quantum sensors. That's being, developed for the next decade. Those things have relatively low technological readiness level at this point, but they're being matured. Some test missions are going to be flown in a few years. So these sensors will shrink and will just allow to have more of these measurements so we can reduce the latency, we can get better coverage, we can get better resolution, and just make this data product even more relevant. So those are just a couple of examples how the technology is advancing and maturing over time.
Oh, that sounds awesome. Another question for you from a colleague is, why are the graphs in your graphs in Greenland and Antarctica? Yes, why the graphs of Greenland are decreasing so much faster than Antarctica? And he means this in terms of like depletion of the glaciers.
The rate, yeah. So why is the rate, the mass loss rate, so different? Yeah. So good question, right? So the mass loss rate here is in aggregate total. It's shown up here. It's about 270 gigatons per year in Greenland and around 140 or so for Antarctica. The reason is while Antarctica is much bigger than Greenland in terms of the total mass that's there, ice mass, it sits really right on the pole and is actually colder in terms of the climate. So mass loss is occurring like in these outlet regions here that I had shown. I can see if I can advance this map a little bit. Maybe it'll load, maybe it won't. We'll see. But so overall, it's still a colder continent, and the mass loss is concentrated here on the coast. So the mass loss potential for Antarctica, so what could eventually melt, is about a factor of almost 10 or so larger, I believe, for Antarctica. But right now, Antarctica has a little, it's about 60% or so of the mass loss rate for Greenland. So Greenland sits at a lower latitude, is a little bit more exposed to ocean currents from the North Atlantic, so warmer, so the eddies can make it there quicker. But we're also observing these warming ocean phenomena near Antarctica where warmer water laps onto the ice shelf or underneath and then leads to these melt events. But it sits at a higher latitude, so it also for almost 6 months a year, right, in the in the dark, right? There's no sunlight reaching it because it's such a high latitude. Those are kind of the main reasons.
Thanks. One more question for you. This comes from Allison. First off, I should say people love your slides. They keep putting in the comments like, where can I get some of your animations? So thank you for putting the QR codes and the links there because we're putting them in there as well. So thank you for that. Allison asks, first off, she says, very interesting. Can you explain a bit more how you are quantifying groundwater? Is it through measurements of surface water?
So the groundwater component, let me see if I can, I'm going to switch to one of these maps here maybe. So when we quantify groundwater, our measurement alone, the GRACE measurement, uses gravity. And the satellites don't know what they're observing in the change. The satellites only see distance changes between them. But it's a little bit like if you think of Newton's apple. So, you drop the apple, it accelerates because of the gravitational field around it, itself and the Earth in this case. So the satellites, they don't drop, they're orbiting, but they're being pulled apart or closer to each other, depending on how much mass is underneath. And at that point, it's all of the mass. And then we look at the change from 1 month to the next. So we still don't really know, is this groundwater or is this surface water or is this snow? And this is where the other observations come in. In order to really isolate the groundwater, we need other information of the surface water. We need to subtract snow, we need to subtract surface water, and we need to subtract soil moisture. Those are kind of the main 3 ingredients. And with having knowledge or other observations of these types, we can isolate the groundwater. So it's really stripping away the other layers from the aggregate total, and then we can have information on groundwater. And if we combine it with other data about maybe land surface deformation, that provides just another, what we call constraint on the groundwater. You learn about the geology, how the water affects subsidence, all these things. So being data rich is really helpful, really important to just learn more about the details as you try to understand, is the groundwater change occurring in the upper layer or in the lower layer? So all that has impact on how we manage water. I hope that answers the question. So there's a lot going on from taking the measurement all the way down to getting to groundwater. There's a huge data pipeline, a lot of knowledge, a lot of people have contributed over time for us to do this.
Gotcha. And last questions for you, Felix. Yes, Allison said it. Thank you very much. It does answer her question. And thank you for your presentation as well. So last question for you. I've studying water mass for many, many years, decades. Is there anything that you see in the data, any trends that would be concerning for you, or anything that makes you feel good, optimistic about where things are going and where have we been in the past?
Yeah, well, that's a great question. So there's actually a paper that just came out about a month ago, looking back at the last 23 years or so. It's in Science. I don't have a figure here right now, but I can send you a link, or we can put that in. I'll put that in the chat later when I get off the stage here. Looking at the trends over the last 23 years, and what we're seeing are emerging kind of hotspots and dry regions. And part of it is related to our active water use. So where humans tap into the aquifer and pump it. Some of that is done in an unsustainable manner, meaning we're taking out more out of our savings account than replenishes naturally. So we know, and because of the data, agencies and stakeholders are increasingly able to devise methods to make that more sustainable by maybe holding water back, letting it drain down, actively pumping it down. So, that's a hopeful sign that we can manage changing precipitation patterns such that it doesn't lead to crises in water. When it comes to other trends on the opposite side, where it just rains more and you get these extreme events with flooding, that means maybe down the road you need to build better drainage or better reservoirs, flood protection, raise levees, or depending, whatever the right method is. So you can take a very sort of, well, no pun, glass half full, glass half empty look at this. I think that the key here is that we take these data, we have them available, and we're being smart and intelligent about applying it to how we use water and how we build infrastructure in this changing world.
Thank you, Felix. And once again, thank you for being here with us. This is something that's very interesting. I've seen Grace for many, many years, but it's always something new when you see new animations like that and hearing the latest. And thank you for explaining the gigaton as well. That always blows my mind about how much water is in 1 gigaton. That is just crazy.
Yeah, I always need to remind myself, because it's such a, I hear the unit, I know about it, but then when you actually try to describe it, it's just, there's no sense for scale for these things often.
Yeah.
Well, thank you, everyone. I appreciated the question, and thanks for the opportunity here to present the great series.
Thank you. And I turn it over back to you, Brian.
All right. Thank you, Peter. Yeah, and thank you so much, Felix, for that great presentation and providing all this great information and lots of new information that I and many of us haven't heard before. So thank you so much. Let me go back here and share my screen. Oop, that went way far. Jeez. Okay. All right. So our next presentation is going to be our own Professor Peder Nelson, Senior Instructor, Senior Faculty Research Assistant 2, OregonView State Coordinator, and CEOAS Globe Partnership Coordinator of the College at the College of Earth, Ocean, and Atmospheric Sciences at Oregon State University on Corvallis, Oregon, in the United States. So many of you know Peter. He has presented often in our campaign. He is on our campaign team, and he'll be talking about Landsat and Landsat Next. And Landsat Next is to be launched sometime late 2030, early 2031 from the Vandenberg Space Force Base in on the Central California coast in the United States. So I'm going to stop sharing. And Peter, I'm going to pass it over to you.
Great. Thanks, Brian. I'm going to start sharing my screen. It'll take a little bit of a moment here to get up and going, but I'm really excited to pick up where that last presentation ended, right? Like this really important piece of how we're looking at gravity on Earth and kind of this arrangement of things. And hopefully you can see this Landsat missions timeline graphic.
Looks good.
Let me know, Brian.
Yep, looks good.
All right, good. And part of this is, I think it's really exciting to think about how long some of these missions have been collecting data. It's I think it's great that GRACE has been around since 2002 and collecting that gravity information that could correspond to some of those measurements that the GLOBE program has created. And and some of that initial piece is that rapid assessment of land cover, right? And land cover change that really Landsat can help us give that longer timeline and even the spatial resolution of maybe what's happening in that GRACE pixel. Because as you saw, those were pretty big areas that are getting measured. And so the details that come from something like Landsat, and especially the time series that we've highlighted over the last 7 years here, is a fundamental piece that can help understand, I think, to that question that Allison had is that surface water that is changing, or is it actually below ground? Are we putting more buildings that might actually have more mass themselves? And maybe we have enough of those that are actually changing the mass of that location. All of these are just really, I think, interesting questions that the GRACE data helps to, give us somewhere to start, right? There's something interesting going on here. And so I want to, for me, one of the things that always helped me is starting to think about going into the future. And so hearing about how the GRACE mission is thinking about data continuity, about how you actually move from one technology to the next technology, is something that is the foundation of remote sensing. And so, each one of these missions has given us insights, and I really appreciated how you start with one type of device and you might actually end up moving into a very different way of measuring that same, say, distance, or the same place on Earth. And so Landsat Next is an opportunity to take advantage of the technology that has advanced since 2021, right? Also, the people who are coming into the career and in thinking about Earth are going to be different than the people that were there in the past that helped to design these missions, or that maybe were the ones that were actually doing that analysis. So I want to really, inspire people here to be thinking about how do you prepare for these upcoming missions? And one of the ways is that we're actually doing, this generational science. And I want to highlight, this really important piece that you can use in your own learning about this change over time. And really importantly, how vital something like the GLOBE database and the GLOBE program and every one of our measurements is to making sense out of these long-term measurements that have been coming from space, whether they be gravity or whether they be more the spectral measurements, that sunlight measurement that GRACE isn't measuring, right? But we get to be out on the ground and actually help to inform what is there. And as we heard from Felix, that is a really important piece. And it can help untangle some of the questions about why that change is occurring in that location. So I want to really highlight, that stewarding this data is one of the valuable pieces that the GLOBE program has provided since 1994, 1995 time period, when that database first came online and we could all start contributing to it. And I think, one of the things that I want to highlight is that, public science requires all of us to be involved. And that's another reason why the open science that happens between that data that Felix was talking about and getting collected there, how it can actually get combined with our data. And also how you can inform and maybe help to design these next sensors. Now, it's really important to recognize that, in the past, we actually have talked about the Landsat Next mission. It was going to be 3 satellites that were going to deal with some of the same sort of issues that we've identified through our science research over that 50 years. And this is really important to understand that, this idea of the Landsat Next constellation has gone through a lot of science rigor and review and input. Well, it was deemed to be too expensive. And so right now, as you see right here on May 2nd, 2025, they are looking at redoing this constellation and how this satellite might contribute to our ongoing understanding of Earth and how we actually instrument our satellites to make spectral measurements that could inform what we're seeing from something like our gravity measurements. Again, getting to that point of, is that surface water or is that actually in the ground somewhere? What is the form of that? Is that ice? Is that liquid water? Or is it in some other state that we've never seen before? Earth is that place that we do that testing. And so I want to highlight that this is one of the things that we've learned over time. Landsat Next was going to be super spectral. It was designed to help fill in these gaps about crop water use. How are those crops using that water that Felix is measuring? What is the quality of the soil and how are we measuring these things? We're all going to build on what we currently have available to us in our current science. And you're starting to hear me get agitated a little bit because this is novel and experimental. There is no satellite up there that currently records in the particular way that this Landsat Next constellation and sensor system and even delivery down to Earth was going to give us. You can see we were going to improve our spatial resolution and actually go from the 30-meter pixels that the GLOBE program and all of us have been working with Landsat for the last 30 years. We were going to try to take that down to 10-meter resolution. And that allows us to really get at some really important things like water quality or water condition. Is that surface water or is that below the ground? And so you start to see how these different measurements, as Felix highlighted, the fusion of all of these that are coming together is the science that has yet to be developed and is emerging and is on the cusp of not happening. And so you can actually be involved in helping to think about what might a satellite be in the future. What do we actually need to measure? You've all been participating or we've been talking about how we measure trees from space for the last 7 years here. So hopefully at this point, you have some understanding of how we use some of this current technology, but also the limitations. We can't identify some of our different species currently because we don't have the measurements. Again, this is where our ground measurements in the GLOBE program really are driving this, because we're the ones that are saying, hey, we've got a maple tree here. We also have an alder tree, and we need to be able to identify the differences there. This is a science problem that our community has actually revealed to the larger science community, and we've asked for systems that help us to discriminate at that type of level. So get involved. Because right now, when you go to the Landsat Next website that we have actually highlighted here in the past, this is what you get. So just watch out and recognize that you can be involved in helping to formulate what the next satellite mission is going to be like that could actually help us within the GLOBE program, measure all of these things, and I think help understand why the gravity is doing what it's doing in these other measurements. And to me, that gravity one is really exciting because, again, it's not a spectral measurement, which is primarily what Landsat is focusing on. Okay, that's my update with Landsat Next. It's really changed since last time we talked about this. And so I just wanted to raise that to everybody's attention because in the next 5 minutes here, I'm going to take us through some of the developments that have happened since we have had GLOBE Observer out there that has allowed us to do these rapid assessment of trees, their conditions, maybe even those surface conditions that can inform why we have the gravity that we do in those locations, if we have enough measurements, right? That's something that we've learned as well. So I'm going to take everybody back to 2019 at our Go on a Trail Data Challenge. And at that time, we only had one global land cover map that we really could use to compare what was happening in our globe country of Argentina, where we have got a lot of people participating, as well as those people in Africa who are contributing there, people and the people who are contributing in our European phenology campaign and various tree activities and measurements over there, as well as across the United States. And we can't forget Australia really was a country and a location that contributed to local understanding of this MODIS land cover derived map. And so again, one of the things that we were waiting for is the technology to get better with Landsat Next or Landsat 8 and Landsat 9, and this ability to get a global land cover map that, again, might help understand why the pixels are doing what they are in the measurement of those gravity field. And so here, one of the things that when we wrote up and looked at this is we actually looked at our surface conditions that everybody was reporting. And I'll just highlight that most of us are not out there when we have the heaviest water. And that is that snow and ice, right? At least on the surface. And so only 3% of our observations during that time were in that snow and ice condition. We had a lot more where it was really dry out there, or maybe a little bit muddy. These are the sort of conditions that can help us understand that where the water is in that column, surface water to groundwater. And so, so just recognize that GLOBE Observer provides you all of this information about what the conditions on the ground, and that, again, might relate back to some of that oscillation that was highlighted in those GRACE measurements. The other thing that I want to highlight is where we were making our measurements across this intensive observation period. And this is really important because we do have a bias of being in grasslands, maybe a little bit in trees, and definitely in urban areas. But, we don't have water on here, so open water or various other things like that, that, again, might indicate where we're making our measurements. And maybe even places that we can't contribute to that understanding because, well, we just don't have a rapid assessment of what's in that land cover in that location. Okay, that was 2019, 2020, 2021. That's what was happening across our GLOBE program is putting all of this data together in anticipation of something that we were really excited about. And again, what we were first looking at this particular land cover data set that came from the Terra Aqua land cover combined data set. And I think it's important to recognize that, you know, similar to those GRACE pixels, coming from that particular series of satellite measurements, we have a 500-meter spatial resolution. That's a really important thing to keep in mind. And what we highlighted in that paper is you need to think about your one individual tree measurement or your individual sample of sunlight through the land cover tool and the pixel size that you're trying to understand. Okay, so that's a really important thing as you get this brand new thing coming to you in your email if you do land cover observations. I just got my very first one, and of course, there's going to be some missing things because of what Brian highlighted earlier on. And I want to stay here a little bit because this is the first time I've seen this out in the public, a satellite comparison table between our GLOBE observer land cover observations and these land cover maps that, again, could help you to understand when you go to that GRACE map and start poking at those pixels. One is you can use this observation latitude, longitude as a way of making sure that you find the same location in those with the GRACE measurements themselves. And you can use this moving forward to make sure that any of the other maps that or data places that you go to, you can get the same measurements as what is presented here or other measurements that you might want to add. As Felix was mentioning, data fusion, bringing together many different satellite measurements across this electromagnetic spectrum or gravity is really the future of where we're wanting to go with all of this. And where this satellite comparison table allows us to go is to, well, at least start getting an understanding of what is been modeled or measured there. I did not label my photos. I just didn't have time that day. You'll find 60%, 67% of our photos and locations in GLOBE Observer are not currently classified. So that leaves us with, I have no idea what to expect in any of these photos, in any of these directional photos. And as Brian was highlighting right now, I can't even see that. So this is a great way to start actually working on a little bit of a hypothesis of, based on these surface conditions, these attributes, what might you find in your photos, right? Importantly, you'll get a little bit more information about the land cover when the website comes back online, right? And you know, but this allows you to then do the third step within GLOBE Observer, or just go directly here and do this accuracy assessment or comparison between what you measured and what you see on the ground and how this particular land cover is shown or modeled in this location. I think, you know, there's some really interesting things that come up, but what I'm told by this group from Langley is that it is urban and built up lands where I did my measurement. Well, that might, again, inform why we're getting the gravity measurements that we were, or what we might see in each one of these photos, right? I would expect to see buildings or asphalt or roads or, you know, something like that. So that's one, you know, this has been something that we've talked about in the past. It is actually current to present. You can find out more about that up here. But one of the things that is also coming down that you'll see that is the big jump forward that I've been waiting for personally for a really long time is this connection to the Landsat, the next resolution below our MODIS, that allows us to start characterizing not just this blockiness, right, but a little bit closer to what I'm seeing on the ground. You'll see there's more decimal points here, right, taking us down to a different level of measurement. One of the things that you'll see here too is that there's two different sensors and actually four different satellites and their sensors going on here. They're measuring at different dates. They're and so they're similar, but they're different. And so, this is one of these things that just became available an hour ago to me. And so watch for us to highlight how to actually make some sense out of this. But what is really exciting is that you can start doing some of this data fusion. And if you click on this option to view the data inside of NASA WorldView, you'll be able to start actually accessing it and maybe even seeing, is there grace of, oh, not in there. If we go into the add layers option here, I'm just going to ask, here is a liquid water equivalent from the GRACE satellite. So I'm just going to quickly turn that on because we had that up, and what I wanted to mention is that this is what you end up getting and where you can go and explore this particular data set. And you'll notice that if you go back in time, there's some data that doesn't exist there. And so just recognize this is a great connection, but these are just visuals, right? But they're the first visuals that we start getting of our location and the 10 kilometers around that spot. If you open up the land cover option, you'll be taken to this view where, again, you might start seeing the land cover map. This is just a visualization, and this can lead you astray when you get these yellow exclamation points that say, hey, you're zoomed in too close. And you can tell that this is not the original data as well, because they have kind of this star approach to it. And so just kind of recognize that you're getting information here, but we want you to do science analysis. You need to take it that next level. And go beyond what you can do here with WorldView, but you can actually go in and do a data download right here and access some of this data. And I want to show you this really quickly here at the end, because at first, it's just like, oh my gosh, there's a lot of data, a lot of information here, but you can set your own area of interest. And this is where knowing your latitude, longitude, and knowing and starting to work with these numbers as a primary way of accessing your data is really, really important. Because you can go in here and you can identify, oh, this is only a 9 megabyte file to actually get this area that I'm interested in researching and studying and understanding that particular gravity field, right? So you can, if you know these numbers, you can go in and you can move this around by hand and get what you're after. But again, I just want to highlight, what happened between 8/13 and 8/19, August 13th and August 19th. That's that missing data that Felix was highlighting, where again, maybe there was a really important event that happened in between these measurements. This again was why we were hoping to have another satellite that would actually allow us to get closer to our sampling rate, and move it down, instead of having 6 days, but get it down to 2 or 3 days, something like that. So, we're making trade-offs between what we have available globally and what we are seeing locally at these locations. And I want to stress how important this will be, because understanding these nuances help us to understand maybe why this looks the way that it does. And I am quite confused actually when I look at this image chip, but then I scroll down and I see an area that I'm more familiar with, and I see a lot of green inside of here, right? and a lot of other features that don't correspond to this blocky appearance. And this can be very much what you see when you look at that gravity field versus what you see on the ground. And so, I wanted to spend a little bit of time going through this satellite comparison table for land cover that is groundbreaking for us. Because you now finally have some of this information at your fingertips that previously you might have had to go searching for a little bit more. But there's a lot of more questions that come up in my mind that really gets answered by this, and that's the way the remote sensing data is. So I'm hoping that you all, when you get your first Landsat comparison or your satellite comparison table for your land cover observations, that you give us, some feedback about how that's working and what you're seeing in your location. And so, to me, that I wanted to spend some time really highlighting how the GLOBE program is really moving science forward, but science is an iterative approach. And we have to plan for 5-10 years in the future if we're going to be able to make the measurements that we are, and be able to keep making those measurements that we have been throughout time here, with especially something as important and foundational as the land cover of your location, which again is one of these things that we're doing with our photos and really trying to update so that other researchers can use that to inform other measurements like that gravity measurement that is really just so unique, but it really needs to have the context of land cover and those trees, right? And are they holding a lot of water or not? All of those things really are the future of remote sensing if we have the ability to keep making these measurements. And I really hope that this community will have the opportunity to dive into this data and really look at these missions and be able to be part of these missions. So again, we're back here looking at ways that we can assess and maybe come up with efficiency or affordability. And so let's be creative as a community here. And that's what I wanted to share with related to Landsat next. And to me, this leads into exactly why we have something like NISAR or some of these other missions, is because they are measuring things that are different than Landsat. They're complementary, yes, but they're different. So Brian, I'm going to turn it back to you and stop sharing my screen right there.
Thanks, Peter. Let me pass it over to Peter if there's any questions. I think I saw one in the chat. Peter Falcon.
Yeah, sorry about that. From Lewis to Peter, what do you do, despite the developments of science research, well supported in data collected by scientific methods, and our politicians don't care about who knows is advising what to do in this case? So I'll try to read that once again. Let me see. Concerning the developments of science research, while supported in data collection by scientific methods, our politicians don't know who is advising. So do you have any thoughts on what to do in those types of cases?
Well, I think yes. And so one of the things that I wanted to start off sort of highlighting here is generational science. How lucky we are to even be having this conversation right now, because other people put together and thought about us. And they put and John Moore, I'm seeing your face on my screen right in front of me, as one of those people that dreamed about sort of this discussion today, and helped us to actually test out, experiment with how humans on the ground can complement our satellite data. And so I think, one of the things is recognizing the public good that comes out of working together as a community, and helping other people understand that it takes forethought. and it takes investment. And sometimes you don't realize what other people are doing until you have a tool like this. Like, oh my gosh, I can measure gravity. I could, I could actually do something that I've heard all about. I can touch it. Some of these things, they're available to us, but maybe they're not available at the moment or the time that we need. And so if some of these things are resonating with you, and you are thinking about, to me, the future generations, future measurements, understanding Earth today, that's great. And I think that to me is one of these really important things, is how just making the data openly available and accessible allows people to find the information they need at the moment that they need it. And as I found, it took me a long time. There was a lag time of about 20 years between when I first started hearing about this information and this ability to actually measure tree growth, and my ability to actually understand it. So I think luckily a lot of what we've been doing in the GLOBE program is now foundational out there. And that's the way that science should be, in my opinion, or the way that I've heard it told me, is we should experiment with ideas and measurements and ways of knowing, but hopefully at some point it becomes operational. And so I take faith in the fact that we have people like who work at the Jet Propulsion Laboratory in Pasadena there that are thinking ahead. They're thinking further ahead than I can. But luckily, I have this spot with the GLOBE program where I can contribute and be ready. And as you see, this time perspective is really, really important. And I don't know how many of us have thought about integrating GRACE or satellite data like that into our science. So there's maybe other new connections that we're looking for that again, maybe other people may not have been thinking about. So it's a long way of kind of saying that I think it comes back that if we can demonstrate value, because these things are meaningful to us, you do end up finding other people who can find resources or ways of doing things that allow us to keep learning from each other. And generationally, that's a really important thing that not everybody gets the opportunity to have. So that's kind of from my view out here as a GLOBE partner. One of the ways that I think about iterative science, that we're constantly searching and researching, and I get to be part of a moment in time. But if I do a good job, other people will be able to keep building on that data, that way of knowing, that science research, and that's the science process that we're celebrating right here.
Let me add to that, Peter, for a second. Peter, you mentioned value, and one of the things when we think about that, one of the things we look at in value is we have with Landsat. First launched in 1972, Landsat 1. I think it was first named ERT-1, I believe, Earth Resources Technology Satellite. If I remember correctly, it was later named Landsat 1. It was the first basically, continuous, systematic high resolution observation of land and looking at change over time. Even though we had TIROS-1 satellite launched in 1960, basically the first view of the Earth. That's one of the most important things that we have. We have this continuous, view of our planet and change over time, since 1972. And that's one of the amazing things that the Landsat, fleet of satellites since 1972 has afforded us, over time. And that's what, the GLOBE program does. We have this continuous environmental monitoring since the mid 1990s, and that forward thinking that you mentioned, Peter, that forward thinking of the folks at JPL, at Goddard, at all the NASA centers, you know, that forward thinking really is what's, you know, promoting, you know, the science, you know, that we're doing. So, you know, it's a great question from Luis. Thank you. You know, it's one of those things that, you know, we're really focusing on, you know, right now, you know, with everything going on. But, you know, the science continues, and it will continue. So it's just, you know, we want to sustain that. And that's what these missions that we're talking about today will do into the future, whether it be NISAR or, you know, Landsat or the, you know, GRACE follow-on and GRACE continuity. So that, you know, that's what we're really focusing on, because, you know, Earth is important. So, yeah. Anything else, Peter, question-wise here? We see, oh, and I did see a really something from John Moore here in the comments. He said, when Peter was talking about this, he said, indeed, you know, try teaching about looking at Earth from space without computers and or the internet. Exactly.
Yes, you made it a lot easier for the rest of us, John. And yeah, so Brian, I really appreciate this, and I think, you know, this will lead into what we get to talk about in September. And, you know, for me, I just want to highlight that we're going to be celebrating 7 years of the Globe Observer land cover tool, that, you know, during that same time. So I hope that everybody here will actually send us some of your own stories and maybe locations and other things like that, if you're interested in also being part of our big celebration about the science that we've been able to do together over all this time. And what, Brian, that will be our 85th webinar?
85th webinar for the campaign. Yeah, amazing. Yep. All right. So what I'm going to do is I'm going to go back to my presentation, my PowerPoint, and I'm not going to play like the full thing from Erica, because I don't want to steal all her thunder for the September 16th webinar. What I'm going to do is I'm going to show an introduction to the NISAR mission. It's about a 3-minute video, because we are already at 36 minutes past the hour. And also, for the folks in India who are joining us, it is really late there, so it's super late there right now. But what I'm going to do is I'm going to show this, and we're going to end with the video on NISAR, because that will bring us into our September 16th webinar, where Dr. Erica Podest will be talking in detail about the NISAR mission. So let me go ahead and share my screen, and we will then go ahead and pop into this now. Current slide. So let me do a little brief thing here. So this is going to be just a brief video on the NASA-ISRO. So that's the NASA Indian Space Research Organization Synthetic Aperture Radar, or NISAR mission. And this was launched on the 30th of July of this year. So just last month at 8:10 a.m. Eastern Daylight Time, or 5:40 p.m. India Standard Time, from the Satish Dhawan Space Center in India, Sriharikota, India. And you're going to hear, like I said, more in detail at our September webinar. And I apologize, but Dr. Erica Podest, she was in India for the launch. And then right after that, she went to Peru, where she is now doing research on some research in the field. So, but she is a research scientist and NISAR Community Engagement and Training Coordinator with the Carbon Cycle and Ecosystems Group at the NASA Jet Propulsion Laboratory, where Peter Falcon and Dr. Felix Landerer are at Pasadena, California. But I'm going to show you this brief video here, and I'm going to do a real sound test here, because Zoom's been strange. But Peter Falcon, tell me if you can hear when this starts, and then I'll restart it.
I can hear it.
Okay, great. I just wanted to make sure, because Zooms were giving me weird things popping up on my screen. So I'm going to show this, and then I'll pull back, and then we're going to end it right after this video, because this will lead us into our September webinar.
NISAR is a collaboration between NASA and the Indian Space Research Organization. NISAR is a radar satellite mission to measure earthquakes and volcanoes, ice sheets and sea ice in forests, ecosystems, and any other thing that's changing at the scale of a centimeter on the Earth.
We are working together, and it's a great mission it is going to be, with two different kinds of radar images that it is going to take, and give a lot of science data for all the science community who are going to look at Earth in a different perspective.
We can effectively make three-dimensional movies of the deformation or the movement of the Earth down to millimeter or centimeter scales.
NISAR is being built as two parts. The payload is being built at JPL, and the second part will be a spacecraft which is getting right now realized at ISRO. NISAR is going to get launched from our launch pad at Sriharikota. The entire world is excited to see what comes out of NISAR.
NASA's Earth System Observatory consists of a series of Earth-focused missions that will work together and complement each other to produce a holistic 3D view of the Earth. NISAR is going to be the trailblazer for this observatory. We're going to learn more about processes related to climate change and assist decision makers and planners to mitigate natural hazards and manage natural resources.
These data will make a major difference in understanding the Earth and helping future generations live sustainable lives.
NISAR is a mix of the two cultures, and it's nice to see that we are almost the same. I'm sure the outcome is going to be something beautiful. We have taken the best of both the worlds and tried to put in NISAR, because we see something very beautiful getting realized every day.
So correct me if I'm wrong, Peter, but I do believe that what you saw there, the antenna, or what they call the bloom, I believe that was just unfurled on the 15th of August of this year. So I believe the data is going to be released very soon. Is that correct, Peter?
Yeah, that's exactly right. Yeah, we're very excited that the boom was up and things look great. So I think we're going to start getting some initial data soon and making sure that's valid, make sure it's measuring what we say it's measuring. And then once we're confident with that data, then release it to the general public so they can use as well. So looking forward to our first flight.
Excellent. I was excited to see that was unfurled, that bloom was unfurled on my birthday. So that was even cooler. So I was excited to see that on the 15th of August.
That's why you remembered it.
Yeah, that's why I remembered it. Yep, exactly. All right, so last slide for the webinar today. As I mentioned, our next webinar will be at 1 p.m. Eastern time, and that's 1700 UTC, 1900 Central European Summer Time, and that 1900 Central European Summer Time. And this will be, as Peder Nelson mentioned, this will be the 85th campaign webinar, and this is the State of Trees, September 2025. And looking back at 7 years of the Trees Around the Globe Student Research Campaign, what we've done and what is to come. And I don't have it listed on here, but there's actually an image of NISAR on here. But we will be starting the webinar with a presentation from Dr. Erica Podest about the NISAR mission in detail. So that video that I just showed you was just to kind of a what do they call it? Kind of like a teaser to bring you into the next webinar. So you'll see that email coming out very soon, inviting you to that. I don't think I sent that one out yet. I don't think I did. I don't remember if I did or not, but you will see that coming out soon to invite you to it. If I did already, sorry about that. I'll send a reminder out as well. But this webinar, once again, will be on Tuesday, the 16th of September at, you see the times here. But once again, as a reminder, you will see the recording for this webinar by Friday, because as I mentioned, the Globe and Globe Observer websites are down for maintenance until sometime tomorrow, the 28th of August. and I don't know the exact time. I don't have that information, but keep going back to the GLOBE website tomorrow to see. They will be up there. An email might be sent out to everyone. I'm not sure, but they will be up tomorrow at some point. So thank you all for being here. I'm going to stop sharing just in case there's anything else in the chat we need to address. But thank you all for being here. And thank you to all the speakers who presented today, to Peder Nelson and Dr. Felix Landerer. And thank you, Peter, for doing the question and answers. We had some great questions today from the community of participants today. So this was a great webinar today. So stay tuned and keep that science coming and taking your observations and continuing that great science that we need. We need that data coming in all the time. So until next time, take care, everyone.